Dunkirk's consulting is an exercise, actually a lot of exercise, in linear regression. Anytime you undertake a linear regression project from scratch, you're going to begin with data. We can see that here with this scenario. Dunkirk consulting, which is to predict the amount of overhead expense. Now, I haven't gotten any farther than the first sentence, and I think I see a hypothesis shaping up, that will be incurred by a consulting contract to develop more accurate bids for future contracts. Okay. Dunkirk has the following data on 11 completed contracts, detailing how long the project took to complete and what the exact overhead expense was. Aha! Here's a table, 11 observations. They are trying to predict overhead expense. That would make it y, our independent variable, based on, apparently from inspecting the table, the length of the project. So this firm called Dunkirk Consulting has a hypothesis that how much overhead expense is incurred by a project depends on how long the project is. Now, what do we need to do? Well, first part of the scenario. Using linear regression, develop a regression formula for predicting overhead expense based on the duration of the project. So what it would look like is y equals a plus b times x, a regression equation, where in our case the x is the duration of the project. You would plug that in here. A and b are constants, and then that would predict the overhead. Oh, right, how are we going to get A and B? Well, we snuck that into the note frames. We have these two particular formulas that we first need to fill out. And those formulas, the formulas for calculating B, the slope in the regression equation, and A, the constant, the intercept in the regression equation, those formulas rely on summary statistics. Like we can see the sum of x times y, the sum of x squared. Oh, right, okay, from scratch, a linear regression, our first task is to gather those summary statistics that we need. Now, the sum of x times y. You know, we have a little bit of room here. Here's x, here's y. I'm going to make another column, x times y, because we're going to need this information. Okay, so in this column, I simply want to note for each project, what is x, the project duration, times y, the overhead expense, or in the case of this first row, 72 times 5,900, I get 424,800. Versus the second project, 158 times 10303. On my calculator, I get 1627874. All right, then keep going. For the third one, 124 times 9054. All right, I got 1122696. And then the fourth project, 96 times 6,644. I got 637,824. For the next project, 152 times 10718. The number I got was 1629136. Then likewise the row below it, 174 times 10332, 1797768. The one below that, x times y, 1091696. The row below that, x times y, 932820. The row below that one, 4988 708. And the row below that one, 479. 486. And finally, the 11th project in the bottom row, 83 times 8,503, 705,749. What was that all for? Just to get that one little thing I need for the formula for the slope, I'm going to add up all these numbers. I add up all these numbers, I get a great big number. The number that I get, I'll squeeze it in right here just for our reference. The sum of sigma x times y, adding up this entire column, 109,48557. Whew. All right, well, we still need several other summary statistics. Now, a couple of them, like if you're looking for the formula, looking at the formula for the slope, are not all that hard to find. They're at least not that much work. For instance, we also need n. N is the number of observations, or n is the number of rows in that table. And, you can see it there, there's 11 projects. And it's not nearly so much work. N is 11. We need the average x. Okay, that would be the average project duration over these 11 projects, or just average these numbers right here. I did that. The average duration I got was 109.909 days. And we also need, you can see it right there, the average y. All right, why don't I put that right here. The average y, average up these numbers right here. What was the average overhead expense in the data? I get 8,665 interesting again, 909. Now, do we have everything we need to actually calculate this regression line? No. We also need, I notice right there, the sum of x squared. Uh-oh. So, I need to create another column, or it's the easiest way to do this if you are actually doing a linear regression equation from scratch. What I need to do is I need to first take each one of the x's, in this case would be the project durations, and square them. Easiest thing again would just be to expand this, make another column. This column here is x squared. Okay, so if you say 72 squared, I get 5,184. Just jot it down. And then, for instance, 158 squared, 2, 4, 9, 6, 4. And then 124 squared, I get, where's my, aha, there it is. I want to stay with the brown ink pen. 15376, and then for the fourth project, square the x, 9216, and then for the fifth project, square the x, I see 23104. For the sixth project, square the project duration. The result is 30276. For the next project, square the duration. I get 15376. The project after that, square the duration. I get 11025. For the project after that, 63 squared is 3969. And for the second to last project, 58 squared is 3364. And for the 11th project, the bottom row of the table, square the x, 6889. Why did I need all of those numbers? Again, I'm going to add up that column because I need that summary statistic. I need the, and I can squeeze it in here, sum of x squared, just the sum of this column, and I figured that out. That is the sum of x squared, 148,743. Okay, now we actually have the pieces that we need to complete the first part of this scenario. Because now we can actually, in essence, work that formula. All we have to do is fill it in. All right, so the slope of the regression line that relates the duration of the project to the overhead expense for Dunkirk Consulting, B equals, well, the sum of x times y, that's that great big number, 109.485557. Okay, so that's that part right there. That's done. Minus n, that's 11, times the average x. Okay, that was the 109.909 times the average y. Okay, that was the 8665.909. All right, that's the numerator. In the denominator, the sum of x squared, what we just found, 148,743 minus 11, that's n, times the average x. Now that's 109.909, except be careful, square it. All right, put that into the calculator. I see 29.722. I'm going to want to kind of mark that. We are going to have a lot of calculations here, and I don't want to lose track of that because I found the slope. I have found the slope of the regression line, 29.722. Now, we're still working on the problem. Oh, we're still working on the problem, but I should mention something. This type of problem where there's a lot of data and there's a lot of calculations, and then you do a calculation like the sum of x squared or the average x, and you take that calculation and you plug it into another calculation. These type of problems are prone to what we call numerical stability. That is to say, you might be working this problem as well, and you go, wait a minute, I'm getting a slightly different answer. I'm getting something like 29.735. I mean, slightly different. Oh, you're not doing anything different or wrong. The only difference is how many decimal places you are keeping each time you do a calculation and then plug it into another calculation. I'm working this as if we had to do this from scratch, which is to say, store these numbers like the average and then put them back into a calculator. If you're doing this in a spreadsheet and you reference a cell that says the average, you're actually automatically storing over a dozen decimal places, and okay, it leads to slightly different answers. Anyway, we still need to finish part A. Okay, so we found the slope. Now let's find the intercept. That's easier to do, but you have to find the slope first because the intercept is the average y, 8665.909, minus, so you need b for it, 29.722 times the average x. So that's the 109.9099. So I did that and I got 5399.2. 5,399.2. Now I keep putting boxes around these as if they're the answers, but they aren't the answers in of themselves, but we're almost there because what is it that the question actually asked, right? What's the linear regression equation? Now we just assemble it. Y equals, oh, okay, you want to predict overhead expense? Take $5,399.20, that number, and add to it 29.722, almost $30, times X, the duration of the project. All right, there we've actually created the expression for predicting future overhead expense. Okay, but that's just part A. Now, what does it ask for part B? Okay, part B. What is the R squared of this linear regression model, and what does that mean? Okay, R squared, the coefficient of determination. What does that mean? Well, before we do the calculations, I can tell you that that is a number that expresses the percent of variation in the actual data, which in our case would be that table, right, that I was writing all over, the percent of variation in that data that's actually explained by that equation that I just wrote down. Now, how are we going to find this number? You say, well, you put the formula right there, right? Well, almost. Actually, the formula that's being displayed right here, see how it says R? This is the correlation coefficient. Oh, you say, well, I don't want that. I want R squared. Right, R squared is just the square of the correlation coefficient. So first we find this, and you can see, okay, we put those summary statistics in and calculate this number, except we're going to need some extra ones. There's some ones we hadn't used before. This one is the sum of x, this one's the sum of y. We didn't calculate that before, because the sum of x is you just add this up. The sum of y is you just add that up. I did that. What number did I get? For x, if you just add on the data table those numbers up, I get 1,209. And the sum of y, if you just add up all the duration, or excuse me, all the overhead expense, 95325. Okay, any other summary statistics in here we haven't seen so far? Yes, there's another one. We calculated the sum of x squared last time, but for this formula you also need, you can see it right here, the sum of y squared. So what I did was I created another column for y squared, squared each one of these, added them up. I'll share the number with you. It's rather long. It features a lot of 8s and 4s. 8, 4, 8, 4, 4, 8, 4, I'm not kidding, 3, 5. Oh, all right. Now, between these summary statistics and the ones that we created anyway to answer the first part of the scenario, now we have everything we need to piece together the correlation coefficient. So let's go ahead and do that. We just want to put each number in the right place. All right, working on the numerator. 11 times the sum of x times y. All right, that's from last time. 109485557. 109485557. Okay, so that's this part right here, minus the sum of x times the sum of y. Oh, okay, well then that's the 1209 multiplied by 95325. Okay, I've got the numerator. The denominator is a little more complicated. Let's work this part right here in these first square brackets. 11 times, that is the sum of x squared. We saw that last time. That's 148,743 minus the sum of x squared, meaning take this number, the sum of x, 1209, and square it. Okay, that's that part. Then the other expression in square brackets, 11 times the sum of y squared. See, I said we would need that. Oh boy. 848448435 minus the sum of y, there it is up there, 95325, but square it. Oh, and when we are calculating this, we do need to remember that that whole thing is under a square root. Oh, all right. Now, if you are doing this along with me, you can check me on this. In the numerator, I get 518,602. Then in the denominator, under the square root, this first expression right here, I got comes out to 174492. You have to multiply it by the result of this expression, which I get is kind of longer, 246077160. So you take this number and divide it by these two numbers multiplied by each other, but take the square root then before you divide them into the numerator. Do that. 0.791455 some odd is what I see on my calculator. And you're thinking, oh, finally. Oh, but wait, we're not done. We're not done. The 0.79, what we found is the correlation coefficient, R, or rho. And what did the question ask? It asked for R squared, the coefficient of determination. We're not done, we're almost done. We just have to take this number then and square it to answer the question. So, if you take this number, 7.1455, and square it, reduces it somewhat, 0.6264, or you can state the R squared as a percent. It's more intuitive that way, like 62.6%. That is the actual, let me box it in, answer to the question, what is the R squared of the model? And then what does this mean? It means, just like I said at the beginning, oh, that in that table, you know, all this data right here, where there is all this variation in the amount of overhead expense in the various projects, 62.6%, I mean somewhat less than 2/3 of that variation is explained by this particular expression that we worked so hard to find. Oh, all right. Now, next part of the scenario. What does linear regression suggest about overhead expense of a future project that is expected to be 110 days long? Oh, this I think we can do fairly quickly. Y equals 5399.2 plus 29.722x. That's our regression equation that we found in the first part of the scenario. To answer this question, we use it. In essence, the 110 days belongs here. Okay, so our estimate would be 5399.2 plus 29.722 times 110. Or we would estimate that a project that's 110 days long is going to incur overhead expense of about $8,668.62. Okay, that would be our estimate based on the regression model. Oh, all right. Well, that at least didn't take all that long. What about the last part of this scenario? In the last part of this scenario, we have another paragraph of information. In the last part of this scenario, what are we being told? A manager at Dunkirk Consulting feels that overhead expense of supply chain consulting projects are generally different from the overhead expenses of marketing consulting projects, because supply chain projects generally require more travel, while marketing projects generally require more spending on external media services. In the table, codes for supply chain projects begin with an A, while the marketing projects begin with a B. Considering this observation by the manager, develop a better way to use linear regression to forecast overhead expense. Using this method, how much overhead expense would be predicted for, again, a 110-day project. If it was a supply chain project, how much overhead expense would be predicted if it was a marketing project. Now, just for convenience in the note frame, the data is repeated here in a little smaller table, and just for convenience, again, those two formulas that we need in order to create a regression model have been staged here for us. What is this last part of the scenario doing? What is the manager actually suggesting? Basically, the manager is suggesting that, this set of data doesn't represent a single population, that there's really two different populations here. There's the supply chain projects, they're this way, and then there's the marketing projects, they're this way. So what would be a much better way to use this same tool, it's the same formulas, to predict overhead expense? You would want to create two separate regression models, one for the supply chain projects and one for the marketing projects. Which means I would basically want to take this data and split it. The ones that begin with A are supply chain, right? The ones that begin with B are marketing. Oh, it's still a regression study, so I'm still going to need the summary statistics. Speaking of summary statistics, okay, supply chain, that's up here. That means if we did this over again, breaking these apart, the supply chain, the n would only equal 5. I'm only counting 5 of these that the code starts with A. And, all right, I went ahead and I averaged the duration of the supply chain projects only. And in that case, I get an average X of 120.4. I averaged the overhead expense of just the supply chain projects. I got an average Y of 8,523.8 versus, remember we're splitting them, marketing. Okay, marketing, N equals 6. There's 6 of those. The average duration there, I get 101.17, basically 101 days. They seem to be slightly shorter than the supply chain projects in general. And an average Y, if you average their overhead expenses, of 8,784.33. So they seem to be, okay, actually, so right away I see there may be something to what the manager is saying just by looking at these summary statistics, because the supply chain projects do seem to be somewhat longer and yet their overhead expenses somewhat lower than comparing them to the marketing projects. All right, anyway, to keep going with this hypothesis, we would need to keep going with collecting the summary statistics separately. Supply chain versus marketing. I did that. Go back to supply chain because I'm running out of room up here. Go back to supply chain. Start again here. We still need, for instance, the sum of X times Y. So if you say this times this plus this times this plus this times this for only the first 5 rows, I get 5, 4, 4, 2, 3, 3, 0, and the sum of X squared for only the first 5 rows, only the supply chain project, 1, 5, 5, 6, 8.8. All right, put these in green into the formulas. I get B equals 57.998 and an A, the intercept, of 1542, which means that the regression model, so to speak, for supply chain projects, just piece them together. The overhead expense for supply chain project is $1,542 plus 57.998, that's the B, times X, the duration of the project. Compared to, remember we're doing these separately, the marketing. In order to set up the regression equation, we're still missing some summary stats. The sum of X times Y, if you say this times this plus this times this for only the bottom 6 rows, I get 5,506,227. And then the sum of X squared for only the rows where the project code starts with B, I get 70899. So take this and what's written in here in purple ink, use the regression formulas to discover the slope for marketing projects considerably smaller. B equals 18.348 basically is what I got. And then A, when you fill out that formula, comes out a lot larger. The intercept for marketing is a lot larger. 6928.1. All right, so just piecing them together, that number 6928.1 plus 18.348x, there would be the regression equation for predicting overhead in the case of a marketing project from the duration. Now, to finish out this particular problem, what is it that it actually asked? Well, here's our recommendation. Here's our recommendation based on a actually inadvisably small number of observations, but nonetheless, about how you could in general predict. It is also asking, using this method, how much overhead expense would be predicted for a 110-day project of each type. Right, so here we'll just employ it, or we'll use that. In the case of supply chain, 110-day project, well, 1542 is what you start with, kind of like a fixed expense, plus 57.998 times the 110. I get 7,920.68. All right, that's what we would estimate overhead expense to be for a supply chain project that's 110 days long. Now, for a marketing consulting project of the exact same duration, well, we'd say 6928.1 plus 18.348 times the same 110, because that's the comparison. And I get that would be more overhead, 8,946.38. is the predicted overhead for a 110-day marketing project. So it is kind of interesting. It seems to bear up the observations of the manager. It looks like the supply chain project is much more dependent, the overhead expense is much more driven by the length, because the intercept is a fairly small number, but then there's a hefty number for each day in the length of the project. Whereas the marketing projects have this big intercept, which is kind of implying that there's a much bigger fixed expense to the project, and it's a little less driven by the length of it. And that might have something to do with hiring that external media provider. Now, the question did not ask, and you do not have to calculate the R-squared. But in case you were curious, the R-squared is a measure of essentially the explanatory power of your formulas. Remember that originally when we pooled all those observations together, the R-squared was what? It was like 62%. It explained 62% of the variation. I went ahead and figured out the R-squared for each of these separately. The one for the supply chain project is 0.965. 0.9. Now remember, R-squared can't get any larger than 1. It's 0.965. And the R-squared for the marketing model is I'm looking at my notes, 0.911. Okay, so it is likewise very close to 1, and both of those are likewise much larger than the original one, which is indicating actually that this probably would be a much better way to predict the overhead expense of these types of projects.